So today is the lecture 8. I am going to start the chemical bonding and molecular structure for the class 12. So today I will discuss about the types of the hybridization. So in the previous class already I told about the hybridization and what is the hybridization and the definitions and the classifications also, and how it happens. That already I have told in the previous class, but today I will discuss about the types of the hybridization. What type of the hybridization is possible for a molecule? Okay, so the types of hybridization. So so hybrid orbitals actually goes to when the hybrid orbitals is goes to the form the bond. Then this phenomena is called the hybridization. So first I will discuss about the sp hybridization. So this sp hybridizations, what is the means of the sp hybridizations? That means that here hybrid orbital is sp. sp is the hybrid orbitals. Okay, so here the sp orbitals is the hybrid orbitals, and these hybrid orbitals is going to form, or we can say that to make a bond, to make a bond. That is the things. That's why this phenomena is called the sp hybridizations. Okay, when it will be the sp2, then the hybrid orbitals will be the sp2. When it will be the sp3, then the hybrid orbitals will be the sp3. So according to the hybrid orbitals, according to the name of the hybrid orbitals, we can say it is a sp hybridization, it is a sp2 hybridization, and it is a sp3 hybridization. Now first is that the sp hybridization. So here is one s orbital is involved and one p orbital is involved. Okay, so two atomic orbitals. So atomic orbital is two atomic orbitals. So when it is a two atomic orbitals, that means that it will have also two sp hybridized orbitals. Two sp hybridized orbitals. So here in this sp hybridized orbitals, there is the two atomic orbitals still present. One is the s, and another is the p. That means that in this sp hybridized orbital there is 50% s character and 50% p character. These are the present for that sp hybridized orbitals. Now how this sp hybridization is happening and what is that actually? These are the atomic orbitals, these are the atomic orbitals, this is the atomic orbitals. So these atomic orbitals are going to is going to make this sp hybridized orbital, and these two sp hybridized orbitals now is going to the make the molecules. How? For example, I am taking here the example is the BeCl2, barium chloride. So here the central atom. So this is the central atom. Okay. So when we will discuss about, when we will go to discuss about the hybridization, then first you have to take the central atom, the electronic configuration of the central atom. So first is the electronic configurations of beryllium. Beryllium electronic configuration is 1s2, 2s2, the 2p0. So 1s2, 2s2, and the 2p0. So this is the simple electronic ground state electronic configuration. So this is the ground state electronic configuration. In this configuration, you can see that this is the valence shell. Okay. Now, excited state, in the excited state, in excited state, what will be the electronic configuration? 1s2, 2s1, and 2p1. So this is like that. So in this, in excited state, so there is the two unpaired electron. There is a two unpaired electrons. Okay. So these two unpaired electrons, actually one unpaired electron is present s orbitals, another unpaired electron is present the p orbitals. So these orbitals now hybridized and gives the two sp hybridized orbitals. Now these two sp, so this is the hybrid orbitals. Now the question is that how these hybrid orbitals are looking like that. So here you can see that one s orbitals and p orbitals. So we know that the s orbital is spherical. So it is a spherical. This is the s orbital, and I am taking there is the px, py, and pz. So three p orbitals is present. I am taking only the pz orbitals. So this is the pz orbitals is present here. This is z axis, this is the y axis, this is the x axis. So this is the pz orbital. Okay, so this is the pz orbitals. Now these two hybrid orbitals, when going to hybridize, and they are making like two sp hybridized orbitals. This is the positive, this is the positive, and this is the negative, this is the negative. So this is one sp hybridized orbital, this is another sp hybridized orbital. So this is the two sp hybridized orbitals of the beryllium. So this is the sp hybridized orbital, this is the one, this is the another. Okay, so in this array, actually in this array, they are making sp hybridized orbital. So what is happening here? The s orbital is the spherical, and I am just this is the, suppose this is the positive and this is the negative. When this p orbitals, when this pz and this p orbitals is going to hybridize that, okay, so this positive positive overlap is possible. We know that this is the phase impossible, or this is the positive possible. So positive positive phase is the possible. That's why this lobe, this positive lobes is the larger in size, and corresponding the negative lobe is the very low. That's why actually. So in this way they are making two sp hybridized orbital, and you see these two sp hybridized orbitals are the linear. This angle is 180 degree, so it is a linear. So two sp hybridized orbital is the linear. Okay, so in this way for the for any sp hybridization, for any sp hybridization, the these two sp hybridized is form, and these are the linear to each other. Now how this molecule is formed? So up to that sp hybridized orbitals, two sp hybridized orbital is forming. Now these two sp hybridized orbitals is going to make a bond with this chlorine and form the molecules BeCl2. Okay, we know that for that chlorine case, it has the 17 electrons, and last electrons is the single electrons. This single electrons is present. It is the present these three p orbitals. So this single electrons also is present the p orbitals. So now I will draw the again this sp hybrid orbitals. So this is like that. Okay, this is the positive, this is the positive. So two sp hybridized orbitals. Another, this is the Cl and this is the beryllium. This is also positive. So this is also Cl. So in this way they are forming the molecules BeCl2. Okay, so this part is for the beryllium. This is the sp hybridized orbital, two sp hybridized orbitals, and these two sp hybridized orbitals is going to make with these unpaired electrons of the chlorine atom, each chlorine atoms which is the present in the p orbitals. So here the one electron is present. So so this is the p orbitals of the chlorine, and this is the another p orbital of the chlorine. So in this way they are the making molecules is the BeCl2. So first of all you have to think about the hybrid orbitals. When I am going to discuss about the sp hybridizations, that means that hybrid orbitals will be the sp. So this is the sp hybrid orbitals. First you have to think about how it will like that sp hybrid orbital, because whatever geometry of the molecules will be formed, that actually belongs to the, that actually comes from the hybrid orbitals. Okay, here here the structure of the sp hybrid orbital, if you see, this is the linear. Okay, that's why the molecules, whatever molecules is forming, this is the bcl2, this is also the linear. Okay, according to geometry of hybrid orbitals, according to geometry of the hybrid orbitals, the molecules also gives that same one. The molecules also gives the same geometry, Okay, so according to the geometry of the hybrid orbitals, the molecules also give the same geometry. Now I am going to discuss about that another hybridization. This is the sp2 hybridization. The sp2 hybridization. First you think about that sp2 hybridization, that means the hybrid orbitals will be sp2. So this is the hybrid orbitals. This is the hybrid orbitals. So 1s and 2p atomic orbitals are involved. So these are the atomic orbitals are involved. So total 3 atomic orbitals are involved. So it will give the 3 hybrid orbitals. 3 hybrid orbitals. Okay. Now you have to think about how the this sp2 hybrid orbitals will be formed. Okay. So just take the one example for that trichloroboran. Okay, so this is the BCl3 trichloroboran. So this is the central atom. So this is the, again I am writing here, this is the central atom. So the boron will have the electronic configuration 1s2, 2s2 and the 2p1. So this is the ground state electronic configuration. Now if I write the for that excited state, so this is the ground state electronic configuration. So 1s2, this is the ground state electronic configuration. But in case of excited state electronic configuration, so it will be like that. So it is the for that excited state. So this is for that excited state. So this is the 2s2 and this is the 2s1 and this is the 2p1. So here if you see that for the in case of the ground state, there is one unpaired electron, the one unpaired electron. But in case of excited state, the 3 unpaired electron. 3 unpaired electrons are present. So now in this excited state, these s orbitals and these 2p orbitals will mixed up and they will form 3 sp2 hybrid orbitals. 3 sp2 hybrid orbitals. Now this 3 sp2 hybrid orbitals, how it looks like that, that is the case. So again, this is the s orbital, this is a positively charged, this is the s orbital. Now we know that px, py and the pz. So 3p orbitals is there, but 2p orbitals will have the 2 electrons, 1p orbital is vacant. So it will not take part. It will not take part in the hybridization. So anyone among these 3p p orbital px and py pz, anyone's will be the vacant, but 2p orbitals will fill up with this 1 unpaired electrons. So what is happening here? So this is the z orbitals, suppose. So this is the pz orbitals. So this is the pz orbitals and this is the px orbital. So this is the px x, and this is the y. So these two orbitals, suppose these two orbitals is px and the pz. These two orbitals are going to hybridize with these s orbitals. Okay, then how it will be formed? So it is looks like that. Actually, this is the s orbital circle. This is the fully positively charged, uh, and this is the one px orbitals, p orbitals. This is the another p orbitals. Then it will give this three sp2 hybridized orbital. The positively charged, this is the positively, this is positively, but it is negative, it is negative, it is negative. So this is the one sp2 hybridized orbital. This is another sp2 hybridized orbital. This is another sp2 hybridized orbital. So here the three sp2 hybridized orbitals are present. This three sp2 hybridized orbital is present in this case. So what is happening here? So these three sp2 hybridized orbitals is formed. Now these three sp2 hybridized orbitals is going to make a bond with the 3cl atom. Okay. So again, the Cl will have the 17 electrons. So one electrons will be present in the NEP orbitals. So here, what is happening? So this is the sp2 hybridized orbital 3. Now 3Cl will have 3p orbitals. So they are forming the bond here. That is for the Cl. That is for also the Cl. But this is the for that boron. This is the 3sp2 hybridized orbital. And this is the p orbital of the Cl. This is p orbital of the Cl. This is p orbital of the Cl. In this way, they are forming trichloroboron BCl3. Now, what will be the geometry? So this is the boron, this is the Cl is present, this is the Cl is present, there is the Cl is present. So the geometry is trigonal planar, trigonal planar geometry. Okay, geometry is trigonal planar geometry. And if you see what I have said, that this one p orbital is the vacant. So boron in this molecules, this one p orbital is the vacant, and this p orbital is not participate in hybridization. Okay, so that's why this is the vacant p orbital. So this is the vacant p orbital is present here. There is no electron. So whatever electron is present in these two p orbitals, these two p orbitals actually going to hybridize with this ds orbital, and they are forming the three sp2 hybridized orbital. And these three sp2 hybridized orbitals now they're going to form a bond with this 3cl, and they are forming the trichloroboron. So if you see the geometry of the hybrid orbitals is also the trigonal planar. So according to that geometry, they are forming the molecule, the same geometry. Okay. So in this way, sp2 hybridization is happened actually, and the bond angle, if you see that the bond angle is 120. So this bond angle is the 120-degree bond angle, because we know that for the trigonal planar geometry, for that geometry, the angle between Cl boron and the Cl is the 120-degree. So here in this way actually sp2 hybridization is formed. Now I am going to the another hybridization is the sp hybridization. Sorry, sp3 hybridization. Now this is the again this is the sp3 hybridization. So you see that this is the sp3 hybridization. So that means that this is the hybrid orbital. So this is the hybrid orbitals. Okay. So this hybrid orbitals, in this hybrid orbitals, one s orbital is present, three p orbital is present. So total orbitals is the 4. So it is forming 4 sp3 hybrid orbitals. 4 sp3 hybrid orbitals. Okay. So now the question is that how this sp3 hybrid orbital is forming. That is the case. But for examples, I am taking here CH4 methane. Okay. So carbons, the electronic configuration is 1s2, 2s2, 2p2. So this is the downstream electronic configuration. So this is the downstream electronic configuration. Now in the excited state, the electronic configuration is what is happening. These electrons will push to that position. So this is the excited state electronic configuration. So in this ground state electronic configuration, this 2 unpaired electron is present. But in this excited state electronic configuration, the 4 unpaired electron is present. 4 unpaired electron is present. Now this is the valence shell. So the valence shell is equal to 2s2 and this is the 2p2. But in this case, the valence shell, in this valence shell, the electron is 2s1 and the 2p3. Okay. So whatever I have told in previous class, from that knowledge I can say that hybrid orbitals actually forms the whatever atomic orbitals are present in the valence shell. So here the s and the 3p orbitals is present. So these 3p orbitals and 1 s orbitals will mixed up and they will form the 4 sp3 hybrid orbital. Okay, so now the question is that how these 4 orbitals are mixed up and how they are forming actually. So here the s orbital is spherical, we know that again. So this is the coordinations. I am just drawing x-axis and y-axis and z-axis. So this is the x, this is the y, and this is the z. Okay. So when these 3p orbitals are going to hybridize with this s orbital, because why these 3 orbitals will go? Because in these 3 orbitals actually have the unpaired electrons. Okay, any p orbital is not vacant. So that's why these 3 p orbitals will go, they are participated in this hybridization. So this is the px orbitals. This is the py orbitals, and this is the pz orbitals. Okay, so when they are going to hybridize and they are forming this type of hybrid orbital, this type of the 3 sp3 hybrid orbitals. So this is the sp3 hybrids orbitals. 3 sp3 hybrid orbitals. Sorry, these are 4 sp3 hybrid orbitals is present. So if you see the geometry of these sp3 hybrid orbitals is the tetrahedral. So the geometry is tetrahedral. Okay, the geometry is the tetrahedral and this angle will be 109.8 degree. So now the H4, now the 4 hydrogen is present. We know that 4 hydrogens will have the 4 s orbitals. So when they going to that bond with this 4 sp3 hybrid orbitals, they will form like that actually. They are forming this bond. This is s orbital, this is s, this is s, this is s. But this is the sp3 hybrid orbital, this is the sp3, this is the sp3, and this is also the sp3. Okay, so in this way, so this phenomena is called the sp3 hybridizations, but they first this carbon is forming 4 sp3 hybrid orbitals. So if you see that for that sp3 hybridization, one s orbital is involved, but 3p orbital is involved. So the s character is 25% s character, 25% s character, and 75% p character. Okay. Now, for example of that NH3, for that sp3 hybridization of the, for example, the NH3 molecule. Uh, so first you have to note out that this is the central atom. Nitrogen is the central atom. Okay. So the nitrogen, the electronic configuration is 1s2, 2s2, and 2p3. Okay. So this is actually for the downstate electronic configuration. This is the downstate electronic configuration. And so if you see that downstate electronic configuration, that one, s orbitals, has that one pair electrons, and p orbitals will have the one three unpaired electrons. Okay. Now, in this case, what is happening? In the hybridization, the p we already I have told that in a valence shell, whatever orbitals is present, so these orbitals will actually take part in the hybridizations. But you have to note that also lone pair takes part in hybridization. Okay. So lone pair also take parts in the hybridizations. So here the lone pair is present in the s orbitals. Okay, and the 3 unpaired electrons is present in the 3p orbitals. So these s orbitals and the 3p orbitals is forming the 4 sp3 hybridized orbitals, and these sp3 hybridized orbitals now is going to if you see that these sp3 hybridized orbitals, how it is looks like. For that ammonia case, the sp3 hybridized orbitals is like that. Okay, so this is the sp3 hybridized orbitals, 4 sp3 hybridized orbitals. But among these 4 sp3 hybridized orbitals, one sp3 hybridized orbitals contains a lone pair. It is content the one lone pair. And another sp3 hybridized orbitals, this is sp3, this is sp3, is content one unpaired electrons. So now this hydrogen s orbitals is coming, they are forming the bond with this another 3 sp3 hybridized bond. This is the sigma bond, this is the sigma bond, this is the sigma bond. Okay, so here the 4 sp3 hybridized orbital. So among these hybridized orbitals is already contain the one unpaired electrons. So remaining that remaining so the remaining the 3 sp3 hybrid orbitals is take part in bonding of that NH3 molecule. So that's why it is structure. So this is the lone pair is present here. This is hydrogens, this is hydrogens, and this is hydrogens. But it will have the geometry is tetrahedral. It will have the geometry is the tetrahedral. But the angle, if you see that, we know that for that angle is the 109.5 degree. But here the lone pair bond pair is interaction is there. Bond pair and the lone pair interaction is there. So due to that interaction, actually repulsion, sorry, this is not the interaction, or we can say that this is the repulsion. So due to that the repulsion, this angle will be have, and also the bond pair also the bond pair repulsion is present here. So due to that the repulsion, this angle is goes to down 107 degree. Okay, so that's why for that ammonia case, you will have not the perfect the geometry is a tetrahedral, but it will have the geometry the tetrahedral, but not according to that sp3 hybridized orbital. So the another example, if you see that water case, OH2. So here the central atom is the oxygen. So oxygens will have the geometry 1s2, 2s2, and this is the 2p4. So this is the 2s2 is there, and this is the 2p4. So in that case also, if you see, we need the two unpaired electrons. So because two hydrogen because the two hydrogens, we need two unpaired electrons to make two sigma bond. Okay, so this is another hydrogens, this is also another hydrogen is coming out. So here also what is happening is the sp3 hybridized orbitals, but among these four sp3 hybridized orbitals, there is one unpaired electron, this is one unpaired electron, sorry, this is the lone pair present, this is the also lone pair is present. But among that four sp3 hybridized orbitals, so two hybrid orbitals contains the two lone pair, and another two hybrid orbitals contain the one unpaired electron. So now these two hybrid orbitals is going to form the bond with this hydrogen. Okay, so there is the two hydrogen is present. Okay, so now this is the oxygen atom. So this is the oxygen atom. So oxygen atoms has the sp3 hybridization. So 4 sp hybrid orbitals is present, but among these 4 sp3 hybrid orbitals, 2 sp3 hybrid orbitals contain the two lone pair. So remaining the two sp3 hybrid orbitals actually going to bond with these two hydrogens. So that's why they are forming the bond, hydrogens bond for that water molecules is like that. The two lone pair is present here. Okay, so here also lone pair bond pair and bond pair repulsion is there. So that's why this bond angle is 104.5 degree, but the real tetrahedral case the bond angle is 109.5 degree, but due to that bond pair repulsion and bond pair lone pair repulsion, this angle is goes down to 104.5 degree. Now I am going to discuss about the another molecules like CH3 CH2C6. So this is the ethane molecule. For that ethane molecules, how it will be that actually. So this is the central atom. So there is a two central atom, but I am taking the one central atom. This is a carbon. 1s2, 2s2, and this is the 2p2. So electronic configuration is like that. This is for the ground state, but in case of the excited state, this is the electronic configuration in the excited state. So if you see for that methane molecules, for each carbon, 3 hydrogen atoms. So 3 hydrogen atom, for the 3 hydrogen atoms, we need that 3 unpaired electrons. So 3 unpaired electrons is present, but one unpaired electrons also is present. Unpaired electrons is needed to make a bond with another carbon. Okay, so that's why in excited state it will so this excited state actually will take this excited electronic configurations actually will take the bond formation here. But so 1 2 3 4, so here the carbons will have, so if you see 1 2 3 4, so 1 s orbitals and 3 p orbitals. So the hybridizations will be the sp3, but it will the 4sp3. 4sp3 orbitals will be there. So it will. So this is the carbon. So this is the another sp3 hybrid orbitals. This is the another. This is the another. This is the another. So this is also the sp3 hybrid orbital. This is also sp3. This is also sp3. This is also sp3. Okay. So this is for the one carbon. For that another carbons also will have the same. Will have the same the sp3 hybrid orbitals. So it is looks like that actually. This is a carbon. Okay. So this is sp3 hybrid orbital. So all are the orbitals is the sp3 hybrid orbitals. So for the each, so for that carbon atoms, 4sp3 hybrid orbital is there, but among these 4sp3 hybrid orbitals, one sp3 hybrid orbitals will make a bond with this another sp3 hybrid orbital of the another carbon atoms. So that's one, and the remaining these three sp3 hybrid orbitals will go to the make a bond with this hydrogen atom. This is for the hydrogen atom, and this is for also the hydrogen atom. So similar case for that molecules also, for that carbon also. Okay. So this is the sp3 hybridization. This is also the sp3 hybridization. So each carbons will have the geometry also the tetrahedron. Okay. So this is case for the ethane molecule. Now for ethylene molecule C2H4. Okay. So this is for the C2H4. So for that carbon case 1s2, 2s2, 2p2. So this is for the ground state. But if you see, first you have to know that how many unpaired electrons you need. So for that each carbon atom, how many unpaired electron is needed? That is the question. So here the two carbon is present. So every carbon is needed the three unpaired electrons. Need the three unpaired electrons. Why? Because if you see, it needs the two unpaired electrons, because every carbons will have here the carbons will for that two unpaired electrons, one unpaired electrons for that hydrogen case, another hydrogen unpaired electrons for that another carbon. Okay. So how it is? So we need that two unpaired electrons. Okay. So here already two unpaired electrons is present. But this is the ground state. If I going to the excited state, that's one. So these two unpaired electrons is the needed for that sigma bond. Okay. So it is looks like that actually. So so for that also, anyone, any four, among these four, actually among these four, we need the two. We need the two unpaired electrons for that two sigma to form the sigma bond. Okay. Another point is that very important point, that the pi bond is not involved in hybridization. It's not involved in the hybridization. So we will not take the pi bond in the hybridization. So what is happening here? So for that each carbon atoms, the excited state electronic configuration is like that. So this is the for the excited state. So this is electrons for that another carbon, and this is electrons for that hydrogen atoms. Okay. So similarly, these carbons will have the same. So this is for that carbon, and this is coming for the another hydrogen. So these unpaired electrons actually, these unpaired electrons, they will make actually the pi bond. So how many orbitals are involved here? Two. For that each carbon atom, two atomic orbitals actually involved. This is one s orbital and another the p orbitals is involved. So the hybridizations will be the sp, but two sp hybrid orbital will be formed for that case. So So this is like that actually. We know that sp hybridized orbital is like that for that one. This is for the one, and this is the hydrogen is forming here. This is the hydrogen is forming the sigma bond. So this is the sigma bond. They are the form. So this is sigma bond. They are forming. But another this p orbitals. So this is the p orbital. So this p orbitals actually this one electron is present. This is one electron is present. They are forming the pi bond. Similarly, for that another p orbitals is there. So this p orbitals actually form the pi bond. So this is the pi bond. So it is the sp3. So this is the sp hybridization linear case. Linear case. So the geometry is looks like, you see the geometry for that molecules. This is the carbon, hydrogens, sigma bond is there. So this is the sigma bond. This is sigma bond. This is also sigma bond. This is also sigma bond. But there is two pi bond is formed. So this is the two pi bond. The pi bond, and this is another pi bond is there. This is the another pi bond. So this is a pi one. This is the pi two. Okay. So I have, if I draw the structures like that actually. Sorry, this is for that. This is the case the C2H4. In the previous here also. Okay, so it is like that actually. So this is a sigma bond, this is sigma bond, this is sigma, this is sigma, this is sigma, and this is the pi cloud. This is the pi cloud. This is the pi cloud. So here for that C2H4 actually, sorry, for the C2H4, the hybridization is sp2 hybridization. It is trigonal geometry, trigonal planar geometry. Angle is 120 degree. Okay, but so and this geometry actually for that C2H2. This is for the C2H2 for the sp hybridization. So in this way, you have to first decide. You have to first decide actually for each carbon atoms how many unpaired electron are needed to make sigma bond. Okay, because so this sigma bond and this lone pair actually are involved in hybridization. Any pi bond not involved in hybridization. So here I have discussed about the sp hybridizations, sp2 hybridization, sp3 hybridization. Okay, so in that next class I will discuss about how these d orbitals are involved or the participate in hybridization. Okay, and then I will go to the MOT. So here student, here I will I will stop the class today. Thank you very much.